systems of linear equations, okay, you should have dealt with like systems of linear equations, quite a lot during your high school years, okay. But so most of the, the first part of this course is a review, okay. Probably like starting from like next week, you will see some new stuff, okay. So here, okay, first, what is a linear equation? Okay, a linear equation, okay, with n variables, x1, x2, up to xn, can be written like this: a1, x1, a2, x2, blah blah blah, an, xn equal to b. In this equation, okay, a1, x2, x3, up to xn, they are obviously variables, okay, and the x1 is considered to be leading variable, okay. Here, the leading variable means like it's well. Let me finish the next one, okay. A1, A2, up to an, they are constants and they are called coefficients, okay. So, for example, A1 is the coefficient for x1, A2 is coefficient for x2, and so on. Okay, so so when we say x1 is the leading variable, we normally assume the x1's coefficient is non-zero. Okay, so if A1 is 0, then this term is gone, right? Okay, then we will say x2 is the leading variable. Okay, if a2 is non-zero. So basically, whichever term, okay, in the front that has a non-zero coefficient is called the leading variable. Okay, so it should be difficult to understand. And the b on the right-hand side of the equation, okay, we call that as a constant term. Okay, in linear algebra, we call b as constant term. In some other areas, such as like data analysis, okay, or data science, b is usually called bias. Okay, bias, but they basically mean the same thing. Okay, so assume s1, s2, up to sn are n real numbers. For given linear equation, okay, x1 equal to s1, x2 equal to s2, and so on, xn equal to sn, okay, is a solution of this linear equation if the equation is satisfied. Okay, so this is, we can say this s1, s2, up to sn is a solution of this linear equation. Okay, if we put this, number, these real numbers, to replace those variables, the equation is satisfied. Okay, so this shouldn't be a difficult concept to understand because you guys have dealt with, linear, such a linear equation like very often in the high school year. It's just like you may not remember or you may not realize their English terminology. Okay, now you know. Okay, that's it. Okay, so which are linear equations? Okay, the first one, obviously, 2x minus 3y equal to 4 is a linear equation. It's a very simple linear equation. How about the second one? 3x minus 4xy equal to 0. It's not. Okay, x times y is not, it's no longer a linear term. Okay, and the third one, okay, 3 over y plus 2 over x minus 1 equal to 0 is not a linear equation either. Okay, if you multiply every term with, try to remove the denominator, okay, by multiply every term with x and y, you will see this term becomes 3x, this term becomes 2y, but we have a minus xy. Okay, that term obviously is not linear either. Okay, the fourth one, x squared plus y squared equal to 4. This is obviously a circle, right? This is obviously a circle, and well, with a 0 as the center of the circle, and radius 2. But unfortunately, this is not a linear equation either. Okay, for the fifth one, 2 sine x minus y equal to 14. This is actually a very complicated function. Okay, because x is we are trying to get the sine of x. Okay, so this is obviously not linear. Okay, however, okay, the sixth one, sine 2 times x minus y equal to 14. This is a linear equation. This sine 2 is just one constant. It's just a constant for x. Okay, just a constant for that coefficient for the x. Okay, which is a constant. The sine 2, even though it looks like it's a complicated coefficient, but it is still a constant. Okay, so for these 6 examples, only the first one and the last one are linear equations. Okay, and also we talk about the solutions, right? I mean, for the linear equation 2x1 plus x2 equals to 4. Okay, when we try to put 1 for x1 and the 2 for x2, okay, we get 2 times 1 plus 2 equal to 4. So it's the equation is satisfied. So obviously, 1, 2 is a solution for this linear equation. Okay, so you can replace x1 with a t, and then we have 2t plus x2 equal to 4. So you move the 2t to the right hand side, so x2 equal to 4 minus 2t. Okay, so obviously for any real number t, okay, such making x1 to be t and x2 to be 4 minus 2t will be a solution for this linear equation. Okay, I think this is very easy. Okay, I mean you have dealt with this in high school already. So t in here is called a parameter. Okay, parameter. So again, I mean this knowledge you should have learned that in high school. It's just like the terminology probably is a new thing for you, but shouldn't be difficult. Okay, so now, okay, we have a simple exercise. Assume u to be u1, u2, blah, 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 to un, and v to be v1, v2, blah, 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 to vn. Okay, these are 2 solutions for one linear equation. Okay, a1 x1 plus a2 x2 plus blah 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 plus an xn equal to b. We want to prove that for any real number c, u plus c minus u minus v. Okay, this is a solution of this linear equation. So can you do that? I mean, I actually give you hint, right? Give you hint. Okay. So first, we want to show that the u minus v is a solution of this linear equation. Okay. So how do we do it? Okay. So we know like a u and the v are both solutions of a1 x1 plus a2 x2 blah 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 plus an xn equal to b, right? So according to the definition, solution. Okay, we know, I mean, they are solutions. So, I mean, if they are solution, okay, you know, we replace this, variable with those real numbers. I mean, the equation should satisfy, right? So, okay, so obviously we put u in this equation. We have a1 u1 plus a2 u2 plus plus an un equal to b, right? Nice. Do we have a better? This one is. Let's try this. And we know V is a solution as well. So we know A1 V1 plus A2 V2 plus blah, 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 plus AN Vn equal to B, right? Because they are solution for this linear equation, so we put them there, right? And then, you know, we do a subtraction. Okay, left side, subtract left side. Right side, subtract right side. What happens is that, okay, A1, U1 minus V1 plus A2, U2 minus V2 plus plus AN UN, sorry, this is UN. UN minus VN, and the B minus B is 0. So we have this, right? We have this, right? So that's like, we can show U minus V is a solution for this equation, this linear equation. This obviously is also a linear equation, because this linear equation, in this linear equation, the constant term is 0. The bias is 0. This is the only difference from the original linear equation and this one. Okay. Then we want to prove, okay, U plus C, okay, U minus V, okay, C times U minus V is a solution of blah, 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 blah. Okay, then, okay, first, U, okay, what we want to show is that eventually, okay, let's write down the goal we want to achieve. The goal we want to achieve is that, okay, we want to show A1 times U1 plus C times U1 minus V1. Okay, plus A2 times, okay, the x2 replacing, I mean, by U2 plus C U2 minus V2. Okay? Okay, sorry, there's one. Plus plus AN UN plus C UN minus VN equal to B, right? We want to show this one. This is what we want to show. Because when I say this is a solution of this, it basically means we need to show this one is true, right? So far so good, right? Okay, so that's try to expand this. Okay. So we will have like on the left hand side, we will have A1 U1 plus A2 U2 plus blah 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 plus AN UN, okay, plus C times A1 times U1 minus V1, okay, plus well, let's get the C out of everything. Okay, A2 U2 minus V2 plus da 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 plus AN UN minus VN, right? On the left hand side, you expand this, okay, and then you try to get all these terms first, okay, and you will get this one, the top one. For the second part, this part, you will see there's always a C, right? So we get the C out of the parentheses. And then inside the parentheses, it will be A1 U1 minus V1 plus A2 U2 minus V2, blah, 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 plus AN UN minus VN. Okay, so obviously it's still equal to B, right? The right-hand side is very simple. Okay, so this left-hand side, obviously, is the first, this one, this line, plus C times this one, right? Right? Okay, so this one, okay, plus C times this one, okay, will be the left-hand side. And the right-hand side is a B, okay, plus C times 0, which is 0, obviously, right? So we have this one, right? So if I mark this one as a star, and if I mark this one as a circle, then basically we have star minus plus C times circle, okay, and we get this one, right? So of course, because this is a proof, so when you write it logically, okay, you have when you come up with this part, okay, you should go from this one backward to this one, and then this one backward to this one, and then you are done with the proof. Okay, according to the definition of the solution. Okay, even though when I show you in a reverse manner, but when you write down your proof, it should be, logically speaking, it should be, the order should be slightly different. Okay, if you are in mathematics department. Okay, if I write this like this, okay, like this order, and I show this to the math professor, he or she will give me, okay, 0. Okay, but in computer science, if you write like this, I would say, look ugly, but it's okay. But I just want you to understand, okay, logically speaking, you should go from there backward to here. Okay. Okay. So hopefully, from here, we can I'll give you some exercise, like because we will have 6 exercises, as I mentioned in the syllabus. So on average, we will have like one exercise every 2 weeks. Okay, so the latest, by latest, I will give you the first exercise next week. Okay, probably not this week, not today, but next week I'm going to give you some exercise. Okay. So now, okay, we have done with a single linear equation, and it is very easy to understand what a system of linear equation is. Okay, basically a system of n linear equations in n variables is like this. You can see a11 x1, a12 x2, blah, 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 plus a1n xn equal to b1. A21 x1 plus a22 x2 plus blah, 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 plus a2n xn equal to b2. And so on until am1 x1 plus am2 x2 plus blah, 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 plus amn xn equal to bm. Okay, and you can see that we have n variable. We have x1, x2, xn, okay, up to xn. We have n variables, okay, and we have m linear equations. So these m linear equations form a system, okay, form a system. Okay, so if you are in high school, you know, if you have 2 variables, okay, if you only have 2 variables, okay, and for a linear system with 2 variables, each linear equation can be drawn on a 2-dimensional, coordinates, okay, as a one line, right? As a one straight line. Okay, so if you happen to have 2 linear equations, okay, each one with 2 variables, okay, then there are only 3 consequences. The first consequence is that, okay, these 2 straight lines intersect at the one point, okay? So that point, that intersected point, okay, will be the solution for this system. Because when we say a solution of system, we normally say like we want, we want this, a set of like real numbers that can satisfy all the equations, all the linear equations in this system, okay, at the same time, okay. So obviously, okay, only this intersection, okay, point can, at the same time satisfy both linear equation here, okay. Another situation is that, okay, these 2 linear equations happen to be, the same line, okay, x plus y equal to 3 and 2x plus 2y equal to 6. Obviously, they represent the same line. So in that case, okay, these 2 lines, becomes 1. So any point on this line will satisfy both linear equation. So I mean, the situation on the left-hand side, your solution space, okay, for this linear system, okay, system of linear equation is only 1 point. But the situation on the, in the middle, the solution space will be, the size of the solution space will be infinite, because any point on this line will be a solution for this the system of these linear equations. Okay, And the third situation is when these two lines happen to be in parallel. Okay, they do not overlap. They actually have no point, okay, in common. Okay, in that case, okay, this is the situation, for example, like x plus y equal to 3 and x plus y equal to 1. These two linear equations obviously do not have, possibly have any solution, okay, because they somewhat contradicting to each other, right? So, so anyway, so for this situation, you have no solution. This linear equation has no solution, okay? So hopefully, when you are in high school, you have seen this, all the time, okay? Because, you learn like this type of, how to, understand the linear equation, as like a line on a two-dimensional space, okay? Linking the algebra with the geometry, okay? You have done many such practices, like in your high school. So this is nothing new for you, okay? At least for like a two-dimensional, right? For two variables, okay? For two variables. But, okay, here we would like to prove that the number of solutions of a system of linear equations must be one of the following cases. The first one, exactly one solution. The second one, infinite number of solutions. The third one, no solution. That exactly, express the three situations, okay, on this slide. So, how to prove this? It's not as easy. Because here we need to consider arbitrary case, okay, n-dimensional, okay, because we now have like n variables, okay. So it's at least we cannot draw this situation on a piece of paper easily, right? In the later time when we talk about like solving linear equations, we will come back to this exercise to talk about this. Okay, right now I want you to think about this exercise. Okay, I'm not saying that you can do it immediately for now. Okay. And one thing I would like to, again, it's a terminology thing, okay? I want you to understand. A system of linear equation is called consistent if it has at least one solution. If a system of linear equation has at least one solution, we call such a system to be consistent. Otherwise, if it has no solution, then this linear system of linear equation is considered inconsistent. So these three cases, for these three cases, okay, the first and the second cases are consistent. Okay, that system of linear equation is consistent. Okay, if it fall into the first two cases, but if it has no solution, we call such a system of linear equations to be inconsistent. Okay? Okay. So now you guys understand the linear system of linear equations. Okay. Let's try to discuss like how to solve the system of linear equation systematically, okay? Because we are in computer science, right? So we care about how to solve a problem systematically. We can even write a program to solve any given set of any given system of linear equations. Okay, so the way to do it is like this. Okay, we call this as a row echelon systems. Okay, row echelon system. A system is in row echelon form. Okay, it's in row echelon form if it follows a stair-step pattern, has leading coefficients of 1. Okay, so first we have to make sure all variables are aligned. Okay, and then in equation, the leading coefficient is the coefficient of the first variable. Okay, I should say non-zero. Okay, I should add non-zero. So you see, we have in this example we have 3 variables x, y, and z, right? So the first one, x minus 2y plus 3z equal to 9. The second one is minus x plus 3y. It has no, the z coefficient is 0. Okay, equal to -4. And 2x minus 5y plus 5z equal to 17. So you can line up these variables. Okay, list their variable. I mean, and then okay, you see the first the coefficient for the first variable, okay, of the first linear equation happen to be 1 already. If it is not 1, we can obviously divide the whole equation by that coefficient to make the coefficient 1. Okay, it's not an issue, but I mean, it happened like the first coefficient. Okay, the first leading coefficient of the first linear equation is 1 already. Okay, and then okay, what we can do is that okay, we try to get rid of the x in the second and the third linear equations. So we just add this equation to the second one, okay, because the second one is negative x. When we add this x to the negative x, I mean, it cancels out each other, right? So when we add these two together, the y, 3y minus 2y, we have a y, and then plus 3z equal to, well, 9 minus 4 is 5. So we have y plus 3z equal to 5. And then you multiply the first equation by -2, okay? And then you add this equation to the third one to cancel out these 2x, okay? And then, because we multiply -2, right? So this one becomes 4y. 4y minus 5y, so it becomes like wait a moment. 4y becomes minus 5y is negative y. Okay, negative y, and this negative 6z plus 5z, it becomes negative y minus z. Okay, negative y negative z equal to -1, right? Am I right? Okay. Let me write it down. I mean, just for and then we add up the first one, second one. We get y plus 3z equal to 5. And for the third one, okay, -0, negative y, negative z. -1. Right? Okay, so you use the first equation, okay, because the leading coefficient for x is 1. So it's very easy for you to just like do some manipulation to cancel out the other x, okay, in the other in the following like linear equations, okay, and then okay, so this is done. Okay, once you finish that, this one you don't need to do anything. Okay, fix this, and then okay, now for the second linear equation, the leading coefficient, okay, for y is 1, right? That's great. Okay, it's 1 again. So we try to use that to get rid of all the y's in the following linear equation, which is the last one. So this one, okay, we add them up. So this one will cancel out. This one, when we add up, this will be 2z equal to 4. Okay, and then okay, obviously we want to make now the leading term of the z. Okay, we don't have any. The x and y. Their coefficient are both 0, but the leading coefficient for z is not 1. So we need to change that to 1. So we get rid of these 2. So divide the whole thing by 2. So we get z equal to 2. So that's how we can move from the left-hand side to right-hand side. Okay? Basically, this is how we get this job done. And once we get the equation into the row echelon form, okay, this row echelon form, let me repeat, okay, it's a staircase, okay, it's a stair step, okay, pattern, and the leading coefficient are all 1, okay. Once we have that, it is very easy to solve this system of linear equation, because we do it from the last one, from the backward. We call that backward substitution. Okay, so because z is 2, right? So that one is for sure. And when z is 2, you substitute z by 2. Okay, so y plus 6, equal to 5. So y is -1. Okay, and then y is -1, z is 2. So you put the -1 for y and the 2 for z. Okay, so it becomes x plus 2 plus 6 equal to 9. Okay, so x must be 2 as well. Okay, x must be 2. X must be 1 as well. Okay, because 6 and y is this was 2. 2, 6 is 8. Okay, sorry, x is 1. So you use backward substitution. You can easily get z is 2, y is -1, x is 1. Okay. So, we say two systems of linear equations are called equivalent if they have precisely the same solution set. Okay, if two systems have the same solution set, then we call they are equivalent. Okay, and the operations, okay, that we can conduct on the system of linear equation to ensure, okay, the resulting system is still equivalent include the following 3 operations. Okay, the first one is you interchange 2 equations. The second one is you multiply equation by a non-zero constant. Okay, the third one is add a multiple of an equation to another equation. Okay, so these three operations, okay, will result in equivalent system. Okay, but why is that? We also need to prove that. So, the first one and the second one are relatively easy. So I would just let you guys to practice. Okay. Let me show you how I get the third one done. Okay. Let me remember like how we represent the general system of n linear equation is like this, right? Shoot. I'm out of ink. How about this? Is it clear to you guys? I'm afraid this is not dark enough. Do we have okay, let me try this. Right? Let me be lazy, okay? Let me be lazy. I will just write the first one and the last one, okay? Oh, this is running out of ink. Okay, this one looks better. Okay, we have this system of linear equations. Okay. Then, okay, assume, okay, without loss of generality, okay, let's assume I, multiply the first one by a constant, say constant c, okay, and then add it, okay, to the last one, okay. Add a multiple of an equation to another equation. So the other one, okay, a11 x1 plus a12 x2 plus blah 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 plus a 1 n xn equal to b1. Here I didn't change anything, okay? What I changed is the last one. I multiply this one by a constant c, and then I add it to the last one. So it becomes am1 plus c times a11, okay, times x1 plus am2 plus c times a12 x2 plus plus amn plus c times a1n xn equal to b1 times c plus b1. So it'll become b. Bn, not b1. Bn plus c times b1, right? I multiply the first equation by c and add it to the last one, so which is shown here, right? 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 Any question here? Right? So now I need to show that, okay, any solution here is a solution here. These are the two different systems of linear equation. I want to show any solution here is also a solution here. Okay, and also if I have any solution here, it will be a solution here as well. The system A and the system B, let's call the top system as system A, the lower system as system B. Okay, I want to show any solution in system A will be the solution for system B, but that's not enough. I also need to show any solution in system B is also a solution of system A, because I need to show that these two systems are equivalent. When I say equivalent, I mean like they have their the set of their solution, the set of their solutions are identical. If the set of solution for system A is called SA, then the solution for system B, I call it SB. I need to show SA equal to XB. These two sets are equivalent. I mean, you guys have taken discrete math, right? Yeah, guys have taken discrete math. Is it from me? Or from Professor Tsai? Me or Professor Tsai? Professor Tsai. Okay, how to show two sets are equivalent? You need to show, the only way to do it is that first, you need to say SA is a subset of SB. And then you need to show SB is a subset of SA. If both of these situations are satisfied, then SA and SB are the same, right? That's exactly what we want to show, okay? If there's a solution here, it will be a solution here, okay? It means, okay, SA is a subset of SB. Okay, if there's a solution here, then it will be a solution up there as well. Then I'm showing SB is a subset of SA. Okay, here, so what you learn in discrete math, come into play, right? It's useful here, right? Okay, well, I mean, let's take 10 minutes break. Okay, when we come back, we will continue the discussion. Okay?